The idea is to take control away from the people and give it to automation, computers, hardware, and they will then run everything. And they can run it much faster and much more efficiently than people can. Even really experienced astronomers, we're only human, so we can only do things so fast. And a robotic system that's well designed can go far faster than a person, which means much more data. So that's the entire reason we go to do automated astronomy. So, but there are different levels of it. So here I've defined different levels of a robot. A robot is not just a monolithic thing. There are different ways you can do it. The first level is just a robot. It's a very simple thing that does something you tell it to over and over. So a good example of something like this is the cruise control in your car. You know, you push a button to start it, then it keeps your car at the same speed, which you modify and change if you need to, and then you turn it off. So that's just a very basic robot. A remote robot basically does everything without you controlling it necessarily, but you can change it. And cars nowadays have a lot of this in what are called drive-by-wire systems. And the same thing for airplanes, where the person who's holding the stick or holding the steering wheel will give a command by turning the wheel, but the computer in the car actually figures out what to do based on the conditions while it's driving. But the car doesn't do it on its own. It takes the person telling it what to do. Then you start getting into levels of autonomy where the system will do everything without a person interfering, but it's more simple. So the very simple driving systems like this new automated cruise control that will speed up and slow down and adjust for cars that pull in front of you or for traffic, those are more of an autonomous thing. You don't have to interfere, but you can still stop it if you need to. Then a proper intelligent robot does basically what we do, but again, it's much faster. So it's real decision making. So if we're talking about cars, it would be a car choosing between hitting a school bus and running over the old lady who's walking their dog and trying to make the choice between which one is the one that's going to cause less damage. So that's kind of how robots work. So now how that works inside of astronomy is we have the same set of levels. So the first one is you can consider scripted. So you give a system just a list of observations and it just chews through them over and over, going through during the night, doing the observations. And without any kind of error management, without correcting for anything, it just does the observation. In remote observing, which is a lot of what astronomy is now, you operate the observatory remotely with a person doing it. And that doesn't mean that you're off the mountain. The people who are sitting there running the telescope are really doing remote observing because basically all the professional telescopes nowadays are run by computers. So they type in commands or they click a mouse or something and it goes and does it, but they're in control. Then you start to get into an autonomous, which does the observing tasks, adapts to weather, and it does it without a person interfering. So, but it's still pretty simple at that level. And then you get to intelligent things, which include the ability to select what they're going to observe dynamically. So people still put in the list of targets that we want to do, but the queue scheduler actually picks and chooses what science is going to be done at that time during the night. And the robotic systems will go ahead and fix things if they go wrong, and they'll restart systems, reboot things, possibly even reboot themselves if they have a major problem. So they're a lot more sophisticated. And the instruments, I'm going to talk about two instruments in detail today that I've worked on at Palomar, and they are really intelligent robots. So they cross the line. They're not going to take over the world or anything, but they have crossed the line to being intelligent robots. So when you saw the title of this talk, you probably thought I was going to talk about something like this, robots doing astronomy. Or you might have thought about something like this because it was robots and lasers, and the way 2020 is going, this seems like it's appropriate. But automated astronomy today is really more like this. This is my job, basically. I sit in front of a computer, I type a lot of stuff. We develop the systems so that it can all be computer controlled, and that's a key thing. To think about how we're going to build these systems, we have to do the hardware part with the software in mind. So we buy things, we produce things, we make things that all can be then taken over by a computer and run, through the system. If we don't do that, it's actually a lot harder to do automated astronomy. So, and then just someone has to sit down and write all the software to make all that happen. And a lot of systems are kind of one-offs. We don't really have a standard automated system in astronomy nowadays. So, and then since this is all computer programming stuff, there's a lot of days where it feels more like this when I'm doing automated astronomy work. So, but that's how it goes. So just a quick history, a very, very short history. This could be an entire talk by itself, but just to give you kind of a flavor of how automated astronomy and robots have started to take over the field. Back in the 60s and 70s, people started to develop robotic systems, but they were only the first level, just basic robots. And no real computer control, or if they used computer control, they used punch cards because that's what they had back then. And they had very, very complicated mechanical systems that would make things happen in the right order at the right time. So not really sophisticated at all. And that's how it was until the 1980s, when personal computers started to allow people to observe remotely. So you could set up a computer system and hook it all together with all the telescope stuff, write a bunch of software, and then run everything sitting at the observatory or sitting on your couch at home. But this was still very simple operations, and it was all on small telescopes in this case, meaning the same kind of telescope size that amateurs would be using. In the 1990s, more computer control came in. So most telescopes, the modern telescopes, are all controlled by computer. We run everything through the computer. We're not punching mechanical buttons to make telescopes do things with modern ones. The telescopes themselves aren't autonomous, though. They're still being run by a person. But actual autonomous instruments started to also be developed because once you have the telescope and the instruments under control, then you just need to write the software to make everything be under computer control. It's actually a very steep hill to climb to do that. It's very complicated. You have to think about all the things a person has to do in order to operate the instrument. And people do a lot of things just instinctively. And you have to put all of that in the software in some way, or you have to protect the system at least so it doesn't do something stupid and break everything. And then since 2000, we've started to make things, computers have gotten better, we've gotten more experience, so we started to make things more and more intelligent. One of the big things has really been automated queue scheduling. That's allowed systems to pick and choose what they want to do as they observe. And the instrumentation has also become more complex. I'm going to be talking about two of the most complicated robotic systems that are out there nowadays. All right, so let's talk a little bit about the telescopes at Palomar. So the first telescope installed at Palomar is the 18-inch telescope. I don't know if you can, I don't think you can see my mouse, unfortunately. So you'll just have to, I'll try to point things out as I go. So the P18 was developed in 1936. It did a whole lot of interesting science with supernova, scale of the universe kind of stuff. It discovered comets, including the big one that ran into Jupiter about 25 years ago now. It was decommissioned in the 1990s, and now in that dome, there's just an atmospheric monitor. And that's automated, but it's a very simple robot. A person opens the dome, the system takes images just one after another. There's no real complication how it does it. And then it closes, a person closes the dome in the morning. The P200, when it was built, it was the largest telescope in the world, starting when it started operations in 1948 until 1993. It's computer controlled, but it's all also run manually. So both of those are just systems that people take care of. So now when we start to get into robotic systems, there's basically two other big domes left, but there's been a couple of ancillary things. The first one is actually where I came into robotic astronomy. The 30-meter telescope project was doing site testing. We had to determine where to put the telescope. And so we put robotic telescopes on mountains in Chile, Mexico, and Hawaii. And we put one at Palomar to develop the robotic system for everywhere else. So, and that was my job. And you can see why you need the system to be automated by this picture, because of the horrible weather that's right there. That's water all over the roof. And, you know, so we just hoisted it up there. I spent a lot of time making this system work, basically teaching myself how to do automated astronomy with this telescope. So, you know, it's kind of important to me. So it was there for 3 years. And then, you know, we went on and operated the rest of the system. And that's another talk, TMT site testing. There's also a small dome called the P20. This is an auxiliary dome that's just used for one-off project testing. It's been, you know, used for various things at Palomar. Right now, it contains an instrument called Gattini IR, or infrared. This is a wide field infrared camera. And the idea is that this is scanning the sky in the infrared to look for transient objects. So things that change during the night. This is similar to a project called ZTF, the Zwicky Transient Facility, that I'm going to be talking about in a little bit. But instead of invisible wavelengths, this is looking in the infrared. So it's a small telescope. It's a test bed for a bigger telescope that will eventually be installed in Palomar for testing, and then we'll go down to the, hopefully down to the South Pole to do this, where it's, you know, very cool and the IR sky looks very, very dark. So with that, I'm going to move to the two main automated telescopes at Palomar. The first one is the 48-inch Samuel Ocean telescope, or Ocean telescope. I always say that wrong. This originally started operating in 1948, and it's a very large Schmidt telescope. So in a Schmidt telescope is a design that has the camera in the middle of the telescope. So if you look at the slide here, you can see that up at the top, there's a lens, which for the 48-inch, it's 48 inches. That defines the telescope aperture. Then at the backside, there's a mirror that's 72 inches. So the light beam actually expands a bit. And then it's focused into the center of the telescope, where when it was first built, they used photographic plates. And the reason this is done this way is to give a very large area of the sky. Instead of most telescopes where you have a small area, like with a Cassegrain telescope, this has a several degree field of view. And it's actually about 50-degree field of view, which is huge for a telescope. So it originally did photographic plates. It did major surveys, which I'm going to talk about in a little bit. And then it was automated starting in the year 2000 for some more survey work. And then it was upgraded with a CCD camera system, which was called the Palomar Transient Factory. And that then has now been developed into ZTF, which does the same kind of survey work, large scale survey, that it was originally doing. So the other telescope on the site is the 60-inch telescope. This started working in 1970. It's in the Oscar Mayer Memorial Building. That is not the hot dog. It's different. Make sure that's clear. This one is a Cassegrain telescope. So instead of the instrumentation being in the middle of the telescope, it's mounted on the back end. And this picture is with the old GRB camera on the back of it. This was also one of the first telescopes that was designed to use computer control. So, you know, it still had switches and things like that, but it was designed so that it could be upgraded and use computers in the future. They were thinking about automation at that point. So it's done several things. Probably the biggest thing is the first brown dwarf that it was discovered at the P60. That's probably the most famous thing. It was automated in 2004 to examine gamma ray bursts. And now it's moved on to doing a lot of survey discovery follow-up. So it will observe targets that other big surveys like ZTF find. And the current instrument is called the SED machine, which is a very low resolution spectrograph that looks at transient ZTF finds. So, okay, so that's the playing field of the telescopes. Now I'm gonna move into the projects that I've worked on at Palomar. And I'm focusing this down just on the two main projects I worked on, just simply because I have the most experience about them. But they also give you a pretty good idea of the breadth of the things that we do in automation at Palomar. I couldn't cover everything in a talk, so I'm going to focus on these. So Robo-AO. Robo-AO is an adaptive optics system. And what adaptive optics is basically is a system that measures the atmosphere and removes the effects of it so that we have a telescope on the ground that operates in a similar way to the way it would when if it was in space in terms of the resolution or how sharp the images can be out of it. If you go out on any night and you look up at the stars, they twinkle. And they twinkle because of the atmospheric distortions as the light moves through the atmosphere. So what we do with adaptive optics is we try to remove the twinkling of stars, which makes it the most unromantic area of astronomy that there is. But it's something that we want to do because it's easier to operate telescopes on the ground than to put them into space above the atmosphere. So the key components of an AO system is first you need a rapid readout sensor. So this is CCDs nowadays. And you need something that goes fast enough so that you can take images of the sky. So each image freezes the distortions in the atmosphere. So you get essentially a snapshot of what the atmosphere looks like, and it's frozen. It's not blurred out by atmospheric motions. And to do that, you have to run a camera. So it's taking images about 1,000 times a second. So it's a pretty fast camera system. Then you need something to correct the wavefront of the light. So the wavefront gets mixed around in the turbulence, as you can see in the picture. And that's what causes all the distortion in the blurring. So what we do is we use a deformable mirror. So it's just a mirror where you can change the shape of it and change it in a way so that it's opposite of the effect of the atmosphere. And then the light that comes in with the atmospheric distortion will come out without any distortion. If it was perfect, things aren't perfect because we're lagging slightly behind, but we get very, very close, and we really do get pretty much perfect when the conditions are somewhat good. If they get too bad, you just can't keep up with the atmosphere. The third key component that you need is you need a fast computer or multiple computers that can take all this information from the images and measure all of the distortions and then figure out the math to explain what they are and change that math into the positions of the deformable mirror so that you do the correction. So that has to run at the same rate as the sensor. All of this runs at the same rate as the sensor. So Robo-AO, we do this 1,200 times a second. So every 1,200 times a second, we take an image, do the math, and then move the deformable mirror. So in order to do this, you also need the object you're going to measure. You have to measure something in the sky because we use the light from that coming through the atmosphere to tell us what the distortions are. And there's two ways to do it. You can use just any old star, but you need a star that's bright enough for your sensor to see it taking images that fast. So that normally limits you to 8th magnitude, 9th magnitude. Bigger telescopes, you can do a little bit more than that. But you're and since there's not that kind of star all over the sky, not that bright, it limits where you can look. So we tend to favor, especially for something like Robo-AO, we tend to favor a laser guide star, which puts a laser spot in the sky anywhere you want it. And then you can, from there, do the measurement. And everywhere you move, you have a target. So you can measure your AO or measure the correction for AO. So how do you actually do this? Well, adaptive optics is really complicated. That should be clear from the last slide. And robotic astronomy is also complicated because it takes a lot of effort to make all these things work together. So automating anything that's complicated is challenging. And we were trying to automate two things with Robo-AO. And when we started doing this 11 years ago, people, really thought that we were crazy to do this. And we've been told that ever since. People didn't think that it was even possible. And in their frame of mind, it made perfect sense because AO was on big telescopes. They were very complicated, finicky systems. It took a lot of adjustment to make it work. And, from that perspective, trying to automate something that hard just didn't look like it was possible. But fortunately, we had Christoph Beranek, who was the PI for this, was a postdoc at the time, and he really was seeing a way that this could make a big difference in astronomy. And I was brought in, so we're kind of partners in crime in this. And I had not done AO before, and I didn't think, I didn't know enough about it to know that it was impossible to do, like everybody else thought, which is an advantage sometimes. So the two of us, we really just didn't like being told things were impossible. So we charged ahead and tried to make it happen. So in order to do this, though, we really had to think about what we were doing. And to automate something, you kind of have to start at the base that you want to build a simple modular and robust pieces and then put them together to make a very complicated thing. So it's like building a bunch of Legos to make a dragon that'll, roam around the house and scare the cats. And, you can do this, but you have to think about it ahead of time. You can't do it at the end. And so what we did is we really were smart about what we were doing. We were going to do this on a smaller telescope. We were going to use off-the-shelf hardware, which saved us money and meant we didn't have to do a lot of custom design like other AO systems. And we started right at the beginning with automating or integrating the software right from the beginning. We didn't wait until the end of the project, which happens a lot in astronomy. And that led us to this. This is Robo-AO on the 60-inch telescope. There's the telescope itself is automated. So, it's able to take care of itself if it has a problem. We have the laser guide star, which is the box at the bottom. And this is the inside of the box. It's a UV laser, so you can't actually see it. We have a camera that lets you take pictures of it. And it, beams out into space like that. Since it's a UV laser, it's safe for, airplanes to fly through. Unlike, laser pointers or other lasers, it can't blow up the plane. It's not strong enough to do that. And it can't blind the pilots because it's ultraviolet, so they can't see it. And the laser can't get through the windows anyways. So we can operate, whenever planes are flying around. Then on the Cassegrain mount at the back of the telescope is the AO system. And this is the inside of the AO system. And I'm only showing you this to show you that it's really a complicated system. This was, Christoph's job to come up with the adaptive optics, all the optical systems. And you can see it's very compact with a lot of things going on. All of this, all the optics I didn't have to worry about, but all of the electronics, all the things around it are stuff I had to automate as part of it. And this is the entire point of what we do, is the actual wavefront correction. So this picture is the core of the M3 globular cluster. And this is what every telescope on Earth sees when it looks at this without adaptive optics. The biggest telescopes in the world, the Keck telescopes, Gemini, they all would get this image because we're all limited by the atmospheric distortions or the seeing in the atmosphere. So the reason we do AO is because of this. When you turn the AO system on and you remove the distortions, you get to the limit, the optical limit of the telescope, which is called the diffraction limit. So you have a system that works as well as the telescope possibly can, presuming everything's working right. And the difference between these is very clear. You can see the fuzzy blobs become brighter stars, and there's all these fainter stars in the background, and you can do science on everything on this image. So this is the entire point of why we do adaptive optics at all. What we want to do with Robo-AO is we want to do adaptive optics very rapidly. We want to do really big surveys. Okay, so this is Robo-AO in motion, and it's looking at objects called the Kepler objects of interest, which are exoplanet hosts around other stars that have exoplanets around them that were discovered by the Kepler satellite. And so this is Robo-AO working. You can see the airplanes flying in the background. It's a time-lapse image. Each of the times that the laser is on is about 110 seconds. So, and we're just moving from field to target to target. It's a very small field. Every once in a while, you can see the system stop operating. That's because we have to avoid satellites in the sky. So we're required by the United States and the Air Force to not hit other countries' satellites or our own country's satellites. We really can't damage the satellites, but hitting another country's satellite is an act of war. So you're not allowed to do it. So we just have software in place that, they give us where the satellites are and we avoid everything. So every once in a while it turns off. And every once in a while it turns around and goes to some other place. And that's the Q scheduler intelligently deciding oh, I can't look at this right now. I got to go look at something else, or I can't look at anything because nothing's available. So Robo-AO right now, no one is doing anything. No one is, we had to be in the dome because people were worried about the laser, but we just were sitting there, chatting and watching movies, and this is all Robo-AO doing its own thing. And the whole point of this is that we can do really big surveys, really big surveys. Most AO systems, they do maybe 10 observations a night. They are doing fainter things, but a lot of that time is eaten up by them trying to set up their AO system. And we can do many, many more observations per night than that. So Robo-AO operated for 8 years, both at P60. Then we moved it to Kip Peak outside of Tucson, Arizona. And then it finally ended up on Mauna Kea at the UH Hawaii, or the University of Hawaii 88-inch telescope. It is by far the most efficient Robo-AO or AO system in the world. When we're just operating all of our operations, we do about 21 observations per hour compared to 1. We've done almost 250 in a night, and our overhead is about 80 seconds. Other telescopes using AO systems, it's 5 to 15 minutes, even 30 minutes for them to get everything going. And it's, for us, our overhead, the biggest thing was always the telescopes. And the AO system would only take about 20 seconds to set up. So when we did shorter slews, like what you saw with the recent, or the video, we just would bang off target, one after another after another. We've done many more than 50,000 science observations. I don't actually have an accurate count now. And we've published 42 papers so far. So, and this is what it's like if you're sitting in the dome watching Robo-AO. We're goofing off here, obviously. On the right side of the left picture in the front, that's Christoph, the project PI. Behind him is Nick Law, who other two people are graduate students for at actually all 3 places, Christoph, Nick, and at Caltech. So we just had a bunch of people up there for that observation. All right, so a little bit of science, a little bit of what we've done. Like I said, we're observing the Kepler objects of interest. There are almost 4,000 of those, and we observed basically all of them. We found a total of 559 of them had companions. This is a plot of all the ones that we've found. The only 2 things I'm going to point out here is you can see the limit of the AO system in the diagonal line of stars on the left. That's there because that's the limit of what we can do in how close we can see differences in magnitude or brightness versus the distance between the stars. And the other thing to point out is it's just a scatter plot. There's no systematic thing in the rest of the plot. So we really have covered the regime of things you might expect. So there's a few statistics here. Don't worry about those. But the main thing is, about 16% of these stars have another star around them. Kepler only sees the one star, when in a lot of cases, 15, 16%, there actually was a second star, like this case. So why that matters is you can imagine, Kepler looking at the star like it's a flashlight, and an exoplanet goes in front, so the flashlight turns off or it goes down a little bit while the star's in front. But if you have a second flashlight there next to it, the planet only goes in front of one flashlight. So that means the light change is different because you have to have, this other light source that nothing's happening. So that means the planets physically are a bigger spot in front of the stars. So it changes the characteristic of the planet. That's why we do this follow-up work, and why it's important, so that we understand what exoplanet systems are like. This particular system is also interesting because there's a lot of exoplanets, and everybody was trying to figure out, how do you fit all these? But we found a couple of KOIs where, there were crowded exoplanet systems. There were actually binaries, which means that there may be planets around both of these stars. So we're looking at 2 planetary systems when we look at this individual object. So most of the binaries that we found here were new. They weren't known before. Most of them, these are just optical binaries, but most of them we think are bound. We're going to go back and follow them up and see if they're actually true binaries orbiting around each other. And we have a lot more to do with the data besides that. But our advantage here is the fact that we were able to observe all of these with one unified data set at high resolution, to examine all these and see what the properties are. And that's very powerful. Other people just couldn't touch that. So we did the other really cool pictures that I have, because everything else the Robo-AO does is just points of light, is the planets. So this is Saturn. And that was before, that was the AO system, turned off. And then you can see when it turns on, everything gets much, much sharper. But you can see, the rest of Saturn is kind of wavering like this. And that's because of the really large scale atmospheric motions. So we take these AO, images, which we made into a movie here. And we actually are able to solve for all the distortions and make the pictures like this. So if you go and you look online for a Hubble picture of Saturn, it's going to look a lot like this. Not quite as good because we have a smaller telescope, but that's the kind of quality we were getting for the planetary systems. So this is Jupiter and the moon Io. And I really like this one because you can see all the structure on Io. So we could actually follow Io's structure as it changes over time. And this is Mars. So, and Mars just looks cool anyways. So those are the kinds of science that we do with Robo-AO. We're taking really high quality images of things in the sky. A lot of what we did is examining binaries to determine what they're like. So in the end, we're not done with Robo. We're not done, but what we have to this point, we've got 42 science publications, 6 technical publications about the instrument itself, plus a whole bunch of conference proceedings. We got 3 patents out of it, 4 PhDs with at least 2 more coming. I think I forgot someone in that list. We also, for the first time, we deployed robotic adaptive optics, automated laser operations, which had never been done before, and a new type of IR detector, which I didn't even cover, but it's going to be very important for astronomy in the future for infrared observations. So we also deployed this same AO system on 3 different telescopes, and Robo-AO was meant to be a prototype. It was not an actual instrument. We were just going to demonstrate that you could do automated adaptive optics at some level. So it's been wildly successful compared to what it started with. And we did it very cheaply, $3 million. The bang for the buck, we're like 10,000 times less expensive than the Hubble project, something like that. And that's been acknowledged. The director of the NSF Advanced Technologies and Instrumentation Division said this about us last year, that we had been the most widely acknowledged award that they had ever given. And it's actually a big honor to have done that with the system. It really, we feel like we've garnered a lot of success out of it. And hopefully, this is going to develop into the future. So, and it is. We just retired the prototype this year. We finally retired it. There are a couple of other systems that have been based on the Robo-AO technology that are out there, as well as some that are not adaptive optics, but they're based on the automation side, so the software side. And I'm going to talk about ZTF next. But for Robo-AO, we're now stepping into the future. We're going to build Robo-AO 2.0, which will be on the 88-inch on Mauna Kea. It's going to be coming next year, and we're going to fix all the mistakes that we made with the first one. Yes, we made a few mistakes here and there, but only a few, not that many. But there's a lot of things that we can improve. We can make it better, both on the hardware side and on the automation side. So we're in the middle of building that right now. Hopefully summertime next year, we'll be ready to go and put it on the telescope, and then we'll be back to doing the same kind of science that we've been doing. So, okay, now I'm gonna hop over to ZTF. ZTF, the Zwicky Transient Facility. So what ZTF is it's a survey instrument, and Palomar has a long history of doing surveys. It started back in the 1950s with the Palomar Observatory Sky Survey. And this was a survey where they put these big 14-inch plates into the telescope, and they just took photographic plates of the entire sky, and then they printed those up and mailed them out to astronomers everywhere. Or they even made copies of the plates and sent those around. And astronomers use that to figure out, interesting things to look at, what was in the sky, where things were in relation to each other. They were still using that, in the 1980s and 1990s when I started to go to school. So, and this was really what probably the biggest science thing Palomar did in terms of observational astronomy, up until a while ago, but it was a big deal. So, and then when they automated the telescope, they put in the transient factory. That was a much smaller camera. So now they've gone back, or what we've done is we've developed something that's the equivalent of the POS survey, but with CCDs. So it gives us a huge area of sky, and it's really the precursor of what's going to be the next big thing in professional astronomy, which is the Vera Rubin Observatory, which was called LSST. If you've heard that, it's been renamed in honor of Vera Rubin. And that's going to do what we do, but with a much bigger telescope down in Chile. So ZTF is mounted on the 48-inch telescope. And as I said before, it's a Schmidt optical design. We have a 47 square degrees of sky coverage. So the full moon is about half a degree, to give you an idea of, kind of the scale. You can fit about 15 moons across in the ZTF camera, which you'll see in a minute. The camera, since it's inside the telescope, we can't make one of these gargantuan cameras like a lot of instruments are that are mounted on the back of a telescope. It has to be very compact, but still, we want it to be mostly CCDs. The main reason that we do ZTF is we want to observe transients. That's the entire point, is to look at the temporal universe, to see how the universe changes from moment to moment or night to night. So we, depending on the science program, we have the capability of scanning the entire sky more than once a night. If we just, went back and forth across the sky, we could cover it all more than once a night. Normally, I don't think the science programs really, hammer away quite that much, but normally we get the whole sky every night. It's a small telescope. It's only a 48-inch telescope. So that's small in the professional astronomy world. But the advantage is anything that we find isn't going to be so faint that you can't look at it with the spectrograph. So everything that ZTF finds can be followed up with other telescopes relatively easily. We have 3 filters, which are roughly G, R, and I. I is a little bit redder filter than R, which is sort of red, and G is green. This is really what we're defining as kind of a new parameter space in astronomy. Very wide fields taken with a somewhat rapid cadence. And we do this with a very large mosaic camera. This is an image of the camera CCDs if they were projected on the sky. So that is the Andromeda Galaxy. So one CCD is about the size of the Andromeda Galaxy. You can see PTF over in the bottom left corner with the moon inside of it. And the other one's LSST, the Vera Rubin telescope is in the bottom right corner, which actually uses the same CCDs that we use. And then there's a couple of others. And so ZTF is far and away the biggest survey camera that there is out there. The reason we do this, since we're on a smaller telescope, what we're trying to do is we're trying to get, very shallow in terms of brightness, but very wide in terms of area of the sky and temporal changes. So it's kind of like, since we're in California, or I'm in California, it's kind of like when you think about the old miners, they go out and just, walk through the river and pick up gold nuggets. And that's what ZTF is doing, is just walking in different streams and picking up the gold nuggets. All the other projects, bigger telescopes, better sites, they're going to go and they're going to do the mining. So they're going to go a lot deeper. But a lot of what they're going to find is going to be just more gold. They will find platinum and uranium and all the things that you can find mining. But, we're just looking for those gold nuggets that are really exciting. So this is ZTF on the 48-inch. It's not that exciting. For those of you, if you remember the slide a few ago, there was this cap on the back of the telescope, and this is with the cap taken off while we were doing testing. So all that stuff back there is all the mirror mounts and all the stuff to hold the mirror in place and shape it, and all that's covered up now. So this is a little bit better view where you can see the entire thing. It's kind of hard to take a picture of it inside the dome. And so this is, cutaway through the telescope. We've got the big electronics cabinet that's kind of the size of a refrigerator, bolted to the side of the telescope. We have the camera mounted inside the middle on a new custom spider that we've built to hold on to it. Then there's the shutter up at the top. So, and then on the bottom, in this image, on the bottom, there are the CCD controllers. There's water cooling that goes to everything to make sure it stays cool so we don't overheat the electronics. And then the shutter itself, the shutter is roughly the size of a ping pong table mounted up on the end of the telescope. And the aperture opens up, it's about a 50-inch aperture in about half a second. So it's really exciting when that shutter moves. It makes a big noise inside the dome. Here's a view of the camera, a close-up with the new spider and the camera. The camera's mounted on a hexapod. That's the strut structure that you can see in the middle. You get a better view of that in a minute. And then the camera itself hangs off of that. And then if you look off to the side, there is, an actual robotic arm inside the system. So here's another view. This is our filter exchanger. Okay, remember the camera's big. If we're going to change the filters, we need some way to move these big filters in place. So we have a robotic arm that's, would be a level 2 teleoperated robot from the definitions I gave at the start. And it reaches down into the cabinet that holds the filters at the bottom of this picture and pulls it out and sticks it up on the instrument. So ZTF is an autonomous robotic system that controls a robot. So we're getting into weird levels of robotic stuff here. Here's a picture of the filter, just so you can get an idea of the scale. It's about 15 inches square. So, and this is a movie of the filter in motion. I'm not sure if you can hear it or not, but the clicks that you hear are electromagnets that are used to hold the filter in place. And this is the arm just taking the filter off and sticking it away in the cabinet. So it'll put it away. And this is, our robotic software is telling you what to do and taking it through. So now it moves and it'll grab the next filter, and it'll put it back on. I'm just going to go ahead because I'm running a little short on time. So this is the actual camera itself. Okay, there are 16 CCDs for the science. Those are the big CCDs, and it's a 606 megapixel camera. So your phone camera is like 10 megapixels or so. So that gives you an idea of how many pixels and how big the images are that we have to deal with. We also have 4 focus CCDs. So these are the small ones at the top and bottom of this image. And they're used to measure the focus position of the instrument. So, because the instrument, you saw how big it is. So the instrument can tilt, it can tip and tilt around. If it gets too far out, then we get one line in the instrument, in the images, that's in good focus. Everything else is out of focus in either direction. So we have to measure with all 4 CCDs and then level the instrument so we keep it in focus. And that's controlled by the hexapod that you'll see on the next slide. And then it's just, it's a very compact camera. You can see there's not a lot outside of the CCDs, and that structure that's there is pretty much the minimum. So it's really been well designed to make it that compact. Our engineers did a really good job on it. So this is the camera blown out. So you can think of it as, the most expensive and amazing sandwich you've ever seen. Up at the very top right of the picture is the hexapod. So the camera is mounted to that, and that is controlled by the robotic system to dynamically keep the camera in place. And then everything else is just folded up inside of the camera body. So the camera itself is only like, I think it's 10 or 15 inches deep once it's all put together. It's under vacuum and kept cold at roughly 160 Kelvin. So minus 110 Celsius. So it's a pretty cold system. And it's very detailed work. If you look at just the little CCD assembly in the bottom, you can see there's all kinds of bits and pieces that go into this to hold it all together. So, and then this is the kind of result. This is our first light picture. So our normal images, we don't put them together and make color images from it. Obviously, we did this to make a pretty image. But this is, you know, the Horsehead Nebula in the middle. So this is in the constellation Orion. And you can just, you know, see it's a pretty big scale. This is one of the stars in the belt of Orion. The thing is, though, is that's only one of the images, one of the CCDs that we get. This is the full 16 CCD array. So you can see the 3 stars are the belt of Orion, and in the bottom right corner, that's Orion's nebula. And to give you an idea of the scale, this is the constellation of Orion with our field inside of it. So, you know, if we moved it up or down, it basically fills in the top or bottom of Orion. So every image we take is that big. Like I said, it's about 15 moons across. So you know, it's a really, really big chunk of sky that we're taking. And we take 1,000 images like this a night and process them. So, okay, so let's talk a little bit about what ZTF actually has to do. So I can talk a little about, you know, the robotic system and what it does. It has to operate the telescope, take images with the camera, synchronize the information, all of the information for all of these images, exchange the filters. It has to do guiding and focus operations. It has to send all of the data to Caltech within a minute after the data is taken so that it can be reduced. And then anything that comes out of that reduction, any of those products, then go out to the world, and the world then is looking for alerts, you know, from that process that tells the world there are transients, interesting things that have happened, like supernovas or something like that. It has to keep itself safe from weather and a whole slew of other things. Probably the most challenging requirement that we had was to deal with the observing overhead. Our overhead had a requirement of 15 seconds, which is pretty challenging because the CCD system would take 20 seconds to read out and write data. And, you know, so we had to basically take 10 pounds of dirt and put it into a 5-pound bag. You know, that's kind of what we were doing. And, you know, it's a real challenge, and we were able to meet the challenge just with a lot of smart computer design. So I was hoping to go a little bit more into detail on this, but I'm going to skip through this pretty quickly because I'm running out of time. But this is how we solve the automation problem for ZTF. This is just a diagram that gives you an idea of all the things that ZTF has to do. All the purple circles, those are the hardware pieces that ZTF is talking to. The lighter blue boxes are the software interfaces that talk to the hardware and control it. And then the little gray boxes in the middle, that's where all the magic happens. That's the core part of the robotic system. So on the interfaces, there were basically 3 of us who developed the software. On the CCD interfaces, Dave Hale, who also works at Caltech with me, did the interfacing that talked to the cameras. Most of the other interfaces were developed by John Cromer, who just retired a couple of years ago, who'd been at Caltech for 30 years as a programmer. And then my responsibility was to make the robotic system, make it all work, and make all of these things to come together and operate. So this is kind of what I do. I don't have a good way to show you because all my products are like scrolling logs and things like that. But basically, let me give you a quick summary. There's about 30 of these interfaces, these lighter blue boxes, and each of them is a separate program or a daemon in software nomenclature. So they all run independently. So the robotic system connects to each of them, and there's 2 channels. So each of those inside the robotic system is a separate process that's talking to those channels and sending commands to the different things. And then the robotic system has about 15 of its own processes or threads that are running things. So it's essentially 75 parallel processes inside the robotic system that control this entire setup. It sounds very complicated, and keeping everything straight is a real challenge. But we sat down and we designed it to be a very modular system. And since we made it modular, it means we could actually keep on top of it all and do all of these things in parallel. All these things can be operated in parallel, or with the CCDs, all the CCDs, they can all be operated in sequence, completely in sequence. So everything they do is all correlated and happens at the same time. There's also an entire level of error management. So anything that goes wrong in any of this is handled. And depending on what it is, it may just be a little restart of one of the daemons to a total shutdown of the entire system. It really depends on what's gone wrong. And the entire software side is very efficient. We're limited by the hardware operation, which is the way it should be. The software only adds a few milliseconds for every observation. So we worked really hard to make this so that it works so well. And we're actually going to open source this so other astronomers can benefit from it. So what all came out of this? We observe about 85 science fields per hour in normal operations. So that corresponds to over 1,000 observations during winter nights. Last night we did 808, but they weren't all short observations. We had some longer ones mixed in with that. We've done over 483,000 science observations in a little over a year of total nights since April 1st. And we lose our nights mostly to weather. Every once in a while we lose a night to a technical problem. And we lost about 3 weeks in October 18 just because there was a major camera issue that had to be fixed, which I found highly ironic because the camera failed the night I started jury duty, and it was all fixed and back on the telescope the night I stopped jury duty. So I don't know what that meant. It was really a weird coincidence. But over the nights that we've observed, we've done 670 observations on average per night. That is a ton of science. I mean, our images are 600 megapixels or 600 megapixels. So that's about 600 megabytes of data once it's all handled. All of that comes off the mountain, all of that's processed. There's a huge back end to turn that into science. It's just, this project is massive. And again, there's a whole another talk just talking about how the data is processed. So anyway, so we've been in science operations since March 2018. As I said, we've had very few hardware failures. Nothing's taken us down except for the camera for more than a night. Except for bad winter storms, things like that. People have been very worried about the robotic arm going off and doing its own thing. I do robotics, so I told people it was no worry whatsoever, and we've never had the arm take the filter and fling it around like this or anything. So it's all, the filter arm has actually been extremely reliable through the whole project. Our observing overhead, remember that we had a 15-second requirement and a 10-second goal, and we actually got it down to 8.9 seconds. And then there's settings on the camera that make it wander, or made it so that we had to push it up a little bit. That was just slightly too fast. We download all of the data from one image to Caltech in 45 seconds after the shutter closes, and we've met all of our requirements. The system is actually doing about 10% more science than it was required to do. So that's a big feather in everybody's cap that we've managed to build a system that works that well. So some of the science results. One of the things that we've found is the nearest asteroid. These are just kind of the cool, things that made the news sort of results. We found the nearest asteroid to approach to Earth. That went by a month or two ago. We also found, you may have heard that there's an asteroid that's going to come by the Earth the day before the election. We found that too. So when you start hearing about all that and hoping that it hits the Earth and the election doesn't happen, that you're talking about an asteroid ZTF found. We also found a black hole merger. So two small black holes of a few tens of solar masses of the sun, merged inside the disk of a supermassive black hole in a galaxy, far, far away. And this result was just kind of amazing. You've got a black hole merger, which was measured by gravitational waves from the LIGO Observatory. And then we were able to see the flash from that because it's embedded in the disk here. So the flash from being inside that gas is what we saw. We found the first asteroid that's ever been found that's totally inside the orbit of Venus. It seems like, this is actually a pretty big asteroid. It seems like we should have found it, but observing close to the sun is actually a lot harder than you think. And if you don't know where to look, it's hard to pick up something like this. So we have a program that's designed to look near the sun in twilight, morning and evening twilight, to try to find things like this. We found several asteroids, in interesting orbits in the near or in the inner solar system, but this is the first one we found inside of Venus's orbit. We found what the fastest eclipsing binary white dwarf pair. So a white dwarf is a star that has collapsed down at the end of its life, and the sun is eventually going to be a white dwarf. And a lot of these, there are pairs of white dwarfs, so two stars that are going around each other, and they will slowly creep into each other. And eventually, when they coalesce, if they're massive enough, they become a supernova. So this is a progenitor of a supernova system. It's the fastest in terms of orbit period. So they go around each other in a few minutes, and they will be gravitational wave sources when they get closer. We'll be able to actually measure the gravitational radiation coming off of them. So, and then this is another asteroid. This is the shortest period asteroid, so the shortest year. There's a lot of interesting asteroid comet observations. There's just, ZTF stuff would probably be 3 talks, for all the different kind of science that we're doing. So we're discovering thousands of transients every year, thousands of things that change during the night. There's over 1,000 supernovas discovered by ZTF every year. But the trick that we have to do with our discoveries is we have to characterize them. So that's where the SED machine comes in at the P60, and the P200 is used, Keck, and many other instruments, observatories, and many astronomers around the world are just following up what we do to try to figure out what we've actually found that goes bang in the night. So the future of robotic astronomy at Palomar, there's still many things that are going to be coming and going on. So at the P48, we actually started ZTF phase 2. Phase 1 is ending at the end of the month. We start that next week. So we have 3 more years of ZTF observations. This is a grant from the NSF that's allowed us to continue on. And we're really laying the foundation for how the Vera Rubin Observatory is going to operate when it comes online in 2023. At the P60, SEDM will continue operating during phase 2, and we're developing the next version of it right now. So we don't know, we need to raise money to build it, but we're in the process of actually figuring it out. There's a new project called Winter, which is coming, and that joke is very, very old now. I kind of wish they named it something else. It is going to be an infrared telescope. It's being developed by MIT. It is going to do the same kind of gravitational wave detection follow-up that we do with ZTF, but it'll do it in the IR. And it'll be mounted on a 1-meter plane wave telescope. And then on the P200, we're finally going to have an automated instrument there, which is called SIGHT. SIGHT is a new AO system based on Robo-AO. Now this one is not going to work like Robo-AO. It's not going to make the images perfect. What its job is to improve the seeing. So it's going to take the atmospheric seeing that we see and cut it in half. So it'll make the telescope resolution twice as good as it would be if it wasn't there. And then it will feed that light down into the other instruments that sit on the 200-inch. And it's going to be completely automated. The operators at the 200-inch will be able to turn it on and off, but the idea is that they won't do anything else. It will just go ahead and run itself and turn the laser on and off and keep itself safe and keep the operators safe, and no one will have to think about it. And that's really an intelligent automated system. That's how you want it to work. So as for actually automating the 200-inch, for someone like me, it's just another telescope, and putting proper automation in there, making it all run, it's just a matter of writing the software, for me. Other people, they look at something that big and think it's impossible and really scary because it's going to do something and point at the ground or something like that. And smart design means that you don't have to worry about that, but the emotional component is probably going to be a bigger hurdle for a while. So maybe one day we'll get around to automating this telescope. So, and just one last note, those of us who do what I do, we depend on the staff up there at Palomar. They have to help us. They have to keep the telescopes running. They help us install instruments, solve problems, those kinds of things. And so, you know, they're always really good. They're always very helpful. You know, we're very happy to have them. And you know, even now they're even more stressed now because of the pandemic and all the conditions it puts on the work that has to go on up there. So, and they've still managed to keep the observatory running, and ZTF saw no changes whatsoever because of the pandemic. You know, we were automated, so we didn't need anything except for them to just, you know, kind of close the door and keep an eye on things. And but they've been able to keep, you know, even when we've had problems, they've been able to keep us running. So we're very thankful for the staff up there and what they do. And that is it. Thank you.
Reed, thank you very much. That was a marvelous presentation, and ZTF in particular is absolutely fascinating. To start off, can I ask, you may have said this, I may have missed it, but you know, 30-second exposures in ZTF, what's the limiting magnitude of those exposures?
Usually I think our limiting magnitude is about 21st magnitude, somewhere in there. So we do some observations that are a little deeper sometimes. Up to I think the longest ones we've done has been 600 seconds when someone's pursuing some gravitational wave follow-up source. But mostly we do the 30-second observations, and it's roughly 21st magnitude. So it's not super crazy faint, but it's reasonably faint to see a lot of things.
Well, for those of us who've used, you know, regular backyard telescopes and do astrophotography, magnitude 21 in 30 seconds is pretty spectacular.
Yeah, well, we do have the advantage. It's a 48-inch telescope, which is bigger than pretty much any backyard telescope out there.
Yeah, pretty much.
And the CCDs are much higher quality than anything you're gonna get for an amateur telescope. You know, they're extremely sensitive CCDs. These are very high quality CCDs that we have in the system.
Let me ask, other questions? Anybody?
So Reed, you made the distinction at the beginning of the talk between automated systems, automated robots, and intelligent robots. Am I correct in sort of seeing from what you said that most of the ZTF functions anyway are automated, and the intelligent part comes in things like checking the safety of components and doing automatic restarts? Is that a correct assessment?
Yeah, the automated, you know, it's a little bit fuzzy when you get to that level, because, you know, where you draw that line, everyone's going to have a bit of an opinion. So it's sort of a thing I put together to try to give an idea of the difference. But yeah, the intelligence comes in things like the error manager that, you know, sees a problem and then looks and says, okay, this is what's being reported that's wrong. These are the steps I take to fix it. It's not like AI, right? It's not a holistic thing that says, oh, this is kind of wrong, you know, and it sort of, you know, bumbles along like a person and resets things and does random things until it works. You know, I program in fixed processes for it to fix things, but it can fix multiple things in parallel. The intelligence also comes in on the queue scheduler, you know, which I didn't have time to cover it all, but the queue scheduler, both for Robo-AO and ZTF, they're different queue schedulers, but in both cases, they choose what's going to be observed that night, you know, during the night. The ZTF one, it actually schedules at the beginning of the night and figures out what's going to be done, but it also can adjust if things change. If it runs out of targets, it'll come up with new ones, that kind of thing. With Robo-AO, we actually had to get into you know, into it more because of the satellite issue. We have to dynamically account for where the satellites are in the sky for every observation. So we can't, we can't just put a list of targets into Robo-AO and let it go, because if the laser hits a satellite, we get into trouble. So there's actually a lot more intelligence in that. None of this is AI. AI is the big thing, artificial intelligence, but AI is not, it's not as intelligent as, at least I don't think it's intelligent as people try to make it seem, simply because you have to teach it. So you have to do a lot of things with AI in order to train it to do the one thing you want it to do. And if you do that, yeah, then it could be really powerful. But if you train it badly, it's useless. And if you train it to go and then you want it to play chess, it's also useless. So it's a very, very narrow bit of intelligence there. And but it can adjust and adapt and look at things, based on what it's learned. Where our intelligence is more of a pre-programmed, figure things out, but we've written the software to do it.
Reed?
Yes.
Another question about the ZTF. Is the focal plane flat, or and what's the depth of focus?
So I can't answer the depth of focus one, because I don't know that number off the top of my head. But the focal plane is actually not flat. The original plates actually had to be bent in order, so you would put them in the plate holder that would bend them very carefully, because the plates were glass. And then, the image, in order to be in focus, so it's an optical system with a very wide field. So the focus is actually a curved plane in space. So you have to bend that plane. And so our CCDs, we don't bend the CCDs because that's a very bad idea. What we do is we mount them in facets inside the camera. You can't see that by eye in the images that I showed you, but essentially, the middle ones are pretty flat. The ones on the edges are more tilted. And we had to actually do that experimentally on the sky. We set them up originally, made our best guesses. The best guess was right in about half of or I think the first time it was right in about a quarter of the CCDs. So then we put it back in and we got it right for about half. And then when we had the one camera error, we got 3/4. And the other 4, one of them I think is still kind of off. The other 3 are pretty close. And it's pretty challenging to take the measurements from the sky on the focuser and turn those into tilt measurements mechanically with washers on the CCD. But we've gotten it so that we're meeting our focus parameters, our focus performance that we need to do the science. And that was the most important thing.
Another question, I understood that the ZTF data stream went through the supercomputer in San Diego. You just mentioned Caltech. Is that right? It goes through San Diego?
So the pipeline, the data is transferred off the mountain on a radio signal through the HP REN network, which is what you're thinking of for San Diego. That's where they're based. But it's just, that's the network connection. It doesn't actually go into San Diego and do anything. And there's 2 lines, one that goes down to San Diego, and the other one I think goes further north towards Riverside or something like that. And either one, the data may come through, and then it gets on the internet and comes into Caltech. So
but it's not processed in San Diego.
Yeah, it's not processed anywhere except for an iPacket on the Caltech campus.
Are there other questions? Are there other questions? Reed, that was fascinating. And
yeah,
thank you
thanks. I'm sorry I went a little bit longer than I meant to, because there's always interesting stuff, that I want to talk about with this. So I talked a little further.
So I have one more question, Reed. Have you read the play RUR by Carol Chapek?
Nope, I've never heard of that one.
I believe it was Carol Chapek. He was a Czech playwright, I think in the 1930s, between the World Wars. And I believe he invented the word robot.
Yeah, now I know who you're talking about. So I've never heard the heard his name pronounced. So, but yeah, that's where the word robot comes from.
Well, you might want to be cautious because I'm not going to tell you what the ending of. You might want to read that play. It's an easy read. At the end of the play, the robots do something unexpected.
So,
so you better watch out, Reed.
well, no, I mean, you know, the thing is both with ZTF and Robo-AO, I mean, I wrote the robotic software for both. And they sometimes do things that surprise me in the way that they choose to do stuff and the way things are sequenced. And that's not always a mistake on my part. You know, I mean, sometimes it's just this happens and this little thing over here does something weird. And so the system adjusts for it in order to get through it. And, you know, actually the first time we turned Robo-AO on, you know, we were just completely surprised at how fast it was going, you know, even me. And I can operate Robo-AO, or I could operate Robo-AO at about half the speed the robotic system can do it. And I know all the tricks to make it work. So just the fact that it can zoom through everything as fast as it does is a surprise. The one thing is, it is not going to take over the world. We don't have to worry about that because it doesn't have legs, so it doesn't matter.
And on that happy note, that reassuring note, again, Reed, thank you very much. And I'm gonna end the meeting at this point. Thanks everybody for coming.
Steve, I'm assuming this will also, the talk has also been recorded and will also be available online if we want to look at it again.
Yes, and I will send out notes telling everybody where it is. Okay, great. Thank you very much.
Everybody.
2 weeks from now, we kind of geek out on the 200-inch mirror. Rick Burris and Jeff Solkauer will be here to talk about the surface precision of the mirror and to talk about the mirror support systems. So 2 weeks from now, and we'll see everybody then. Thank you very much.